স্যার যাচ্ছে স্যার।
Okay, good. So we waited enough. Finally, there are like 50 students. 50 জন আসছে মাত্র, 15 are absent. I don't know why. সবাই তো এর মধ্যে বাসায় থাকার কথা। But whatever, I'll start the lecture now. And today we are going to start our discussions on beam design. So today's lecture is like the first step toward designing a beam. So I'll share my screen now in a while, and my advice is you will take a piece of paper and a pen and you take notes, and I may give you some calculations during the class, and after the class I'll give you an assignment. And also I already declared in the classroom that we'll be having an exam right after the vacation. So we'll discuss about the exam and the assignment like at 4 o'clock before we leave the class. So today's class is about beam design. I'm going to share my screen now. Probably I need my digital writing pad today. Just a minute. I'll connect the digital pad now. Do you see my screen now?
Yes, sir.
Yes, sir.
Okay, so we will start our discussion on flexural analysis and design of reinforced concrete beams. First of all, we need to understand what we are looking at now. We will be designing the beams. We will be designing the beams. In my first lecture, lecture 1, I showed a few figures of the beams. For example, this is a beam. So what we will be designing is this thing. These are beams. The horizontal structural members are beams. So we will design them now. Now, if you take a beam out of your structure and look at it carefully, you will see that the beam actually looks like this, something like that. Look at the figure to the left side. So we have concrete, and inside concrete we have these reinforcing bars. First of all, we need to understand some terminologies. the objective of the, like, in the first maybe 30 minutes, in the first half an hour, we will understand the terminologies. For example, this dimension of the beam, which is usually horizontal, is called the beam width, B. We will always denote it with B. For example, if you look at this beam from this view, if you look at the beam from the front, you will probably see a cross section like that. The same beam is drawn here as a three-dimensional, and this is the cross section. This is the cross section. So beam width is here. The same thing. You can look at it in a three-dimensional or whatever. This dimension is called the beam width. Now, you need to, by the way, I need to open another PowerPoint file today. I'll share the file with you today. So let me open a new file. New now. Let's consider today is June 3, no, June 4.
June 4th.
Yeah. So just now you understood the beam width. It's the horizontal dimension. So you need to understand that beam width is usually, assumed. In general, beam width is an even number. So you will find 12 inches, 14 inches, 16 inches, 18 inches, etc. According to BNBC, says beam width B should be greater than or equal to 12 inches, not less than 12 inches. And in most of the buildings, B equal to 12 inches. There is no variation. We always use B equal to 12 inches everywhere in buildings. So the rest, so in bridges, when I write bridges, I also mean flyover, elevated expressway, metro rail, and everything. In bridges, it could be 14, 16, and 18. A beam width larger than 18 is rare. And as I already told you, it is always assumed we do not calculate beam width. So we just assume something for beam width. Okay.
Sir,
What?
sir, I have a question, sir.
What?
Sir, this is assumed regardless of the how many stories the building is.
Yes, regardless of number of stories.
Okay.
The building can be a 5-storied building or 50-storied building. Beam width will remain same, 12.
Okay, sir. Thank you.
Okay. By the way, since you asked the question, I think I need to answer it in brief. The beam size depends on the floor. The beam size depends on the floor load. So beams usually receive forces from the floor. Let me give you, I think I have a better figure in another PowerPoint. Let me open that PowerPoint now. So there you go. It's a small building, but So as you design the beams, you need to understand that it depends only on the floor load. And floor load remains the same in every floor. Floor load, as you understand it, it is composed of dead load, live load, and so on. Wind load and earthquake load usually do not apply on the floors. So floor load is basically dead load and live load. So you understand that every floor will have identical loads. So the beam on this floor, we say FB1, floor beam 1, in every story will have the same dimension. Beam, a certain floor beam at a certain location will have same dimension in every story. So তোমার যদি 50 তলা বিল্ডিং হয়, a certain beam located at a certain position will have the same design. You don't have to design beam for every floor. You design the beam only for a typical floor and you give the design to the contractor. He will construct the same beam at the same location in the same way for all floors. That's the answer to your question. By the way, at the same time, you need to understand that the dimensions of column is dependent on the number of stories. If this is a three-storied building, the columns will be narrow. But if you construct 10-story, for example, having the same layout plan, the columns will be much bigger in size. So size of the columns depend on the number of stories. Even the size of the foundation also depends on the number of stories. But size of the beam and the size of the slab doesn't depend on the number of stories. Okay, that is the answer to your question. I'm going back to my previous discussion. So this is all about beam width. Next, next we'll talk about beam total depth. Beam total depth is simply the beam depth to the other dimension H. That's our beam total depth. Beam total depth is usually calculated. So it is not assumed, it is calculated. You just express it, beam total depth. It is calculated and you express it in integer. There is no strict rule that you have to express it in even numbers, but it's better to express it in even numbers. But odd numbers are possible. People express it in odd numbers, but it's better to express it in integer, not in a fraction with decimal points, because any fraction will provide some extra work, extra manpower on site. So we'll keep everything easy to understand for the contractor and basically for the workers. Next is you need to look at the steel bars. In this figure, you see there are 3 steel bars near the bottom, and there are 2 steel bars near the top. You should understand a few concepts here. First of all, we do not design a beam to have steel bursts at both top and bottom. We don't do that. So what I said is, we are talking about at this moment about the steel area. So we will either you consider the top bursts or you consider the bottom bursts. But bursts must be designed following ACI calculation methods. So this is our purpose. We will design the number of bursts. So when you design the burst, you determine, so this means you determine how many bursts are required and what are the bar sizes. So you determine how many bursts are required and what are the sizes of the bursts. So in our first lecture, I don't know how many of you cared for that, but it's very important. In our first lecture, at the end of the slide, there was this table. I told you that these are the available steel bursts. These bursts are available in Bangladesh and in America as well, and in some other countries. Most of the countries who are in the American bloc, not in the Russian bloc, have these sizes of bursts. So we have bursts in these numbers, 3, 4, 5, up to 18, and these are the diameters. These are the diameters of those bursts, and these are the cross-sectional areas. I told you in the first lecture that you need to remember the cross-sectional areas. You cannot use diameter to calculate the cross-sectional area as pi d to the d square by 4. We do not use that formula. Rather, you will remember these bar areas for all of your future as a student and as an engineer. You need to remember that. All engineers remember these bar cross-sectional areas. So when you design steel bars, you will say two things: how many number of bars you are designing, and what is the size of those bars. For example, I have a few examples here in my PowerPoint. Look at the beam sizes. So we mention usually this way. For example, 4 number 7 bars. So এইখানে 4টা number 7 bar আছে. For example, 6 number 6 bars is mentioned here, which means 6টা number 6 bar আছে. So this way, every beam will be having certain number of bars, and the bar size must be mentioned. We have 16 number 8 bars here. We have 9 number 9 bars here. You should also notice that either we have bars at the top or we have bars at the bottom, not top and bottom simultaneously. So every beam will mention the bar sizes and number of bars. Every beam will mention that. So when you design, you mention the beam width, you mention the total depth, and you also mentioned the number of bursts and size of the bursts. These will come from calculation. We will do this calculation throughout the semester. Puro semester jure, we will calculate only this thing, the beam width, beam total depth, and number of bursts. So let's go back to our discussion. I told you. So now we are talking about steel bursts. So bursts must be designed by following SI calculation method. This means you determine how many bursts are required and what are the burst sizes. This is what you will calculate. Let us come back to this figure one more time. This figure shows that we have bursts at the bottom and at the top. So what is the purpose of the bursts both at the top and bottom? Perhaps I never told you about this thing. These rings, these are called stirrups. We will talk about stirrups after the midterm exam. Stirrups are required to resist shear force. At this moment, we are not considering shear design, so we will ignore that thing. Of course, these things are there, but we are not going to design them. We are designing only the main bars. These are the bars to resist bending moment. So these bars will resist bending moment, and the rings, the stirrups, will resist shear force. And the whole purpose of these two top bars is to hold stirrups. উপরের এই দুইটা বারের একমাত্র কাজ হলো স্টিরাপগুলোকে ধরে রাখা. There is no other purpose for the top two bars. We are using the bottom three bars to resist the bending moment. We will design for bending moment throughout this class and the next class, and maybe up to before we start the midterm exam. Okay, so let us go back and start talking about steel bars. So we may have, for example, this beam has 3 bar areas. That is why I have shown 1, 2, 3 here. So we have 3 number 8 bars. Now, if you remember what is the area of 1 number 8 bars, so একটা number 8 বারের area হচ্ছে 0.79. So steel area here will be 3 into 0.79. So we calculate steel area is calculated as the total So the bars that are resisting bending moment will be calculated as steel area. Steel area is usually denoted by AS. We are talking about steel area at this moment, AS. So you should notice the calculations in all of those slides now. If you have a calculator, I told you to hold a piece of paper and a pen. So now you should notice how we calculate steel area. So we have B and H, and since this beam has 4 has 4 number 7 bars. So steel area is calculated as 4 into 0.6. 0.6 is the area of 1 number 7 bars. Do you understand how AS is calculated? We
Yes,
will
sir.
do calculation throughout this class today. For example, 6 number 6 bars. Steel area is 6 into 0.44 because 0.44 is the area of 1 number 6 bars. So I'm telling you over and over again that you need to memorize these bar sizes. We are using here area of number 6 bars equal to 0.44, number 7 bars equal to 0.6, number 8 bars equal to 0.79. In our beam, usually these 4 types of bars are provided. Beamer bar bolte ei 5, 6, 7, 8. Not smaller than this, not larger than that. So we will mostly restrict ourselves within these 4 bars. So just try to remember them. For the time being, you just remember number 5.31, number 6.44, number 7.6, number 8.79. Just remember these bar areas. It will be helpful for you. Okay. So we calculate AS for every beam. We should notice it here. At the same time, this beam has 16 number 8 bars. So AS is 16 into 0.79. This beam has 9 number 9 bars, and this is our AS. I'm giving you 1 minute to look at this calculation. This slide and the previous slide.
স্যার এখানে 0.04375 আছে, এটা কি এখানে wrong?
হ্যাঁ, এটা wrong, এটা ঠিক করবে একটু পরে। We are talking about AS at this moment. We'll talk about D right after that. তখন ঠিক করে দিব। Just look at the calculation of AS. Do not go beyond that. I have more examples. For example, this one, we have 10 number 10 bars. So AS steel area. AS is steel area. 8 number 9 bars, we have AS. Okay, after we talked about steel area, now we go to the next concept. Next concept is beam effective depth. Effective depth is different from the total depth. The total depth is the total depth. Total depth is from the top to the bottom. You calculate the total depth right exactly from the top surface of the beam to the exactly to the bottom surface of the beam. So from the top surface to the bottom surface, that's the total depth. Effective depth is something different. Effective depth বুঝতে হলে you need to understand a few more things. Number one, let me write them down. It's an online class. I'm not sure if everybody is following properly. So number one, there is a clear cover. Clear cover to protect so you have all the steel bars a bit inside, not exactly at the outer surface. So now please look at the clear covers. We have a clear cover from the outer surface of the bar to the outer surface of the beam. We have a clear cover. Look at the clear cover things now. Clear cover. Sometimes it is called the cover depth. So there is a clear cover. Bursar put a bit inside, not exactly at the outer surface. Bursar put a bit inside. Bursar placed a bit inside, having a clear cover. I think by now you understood what clear cover means. So every beam will have this sort of clear cover. So clear cover is there. Now when I say superstructure, I mean above ground level. And by substructure, I mean below ground level. So usually in a beam which is above the ground, there should be at least 1.5 inch clear cover. And for the beam that are under the ground, there should be at least 2.5 inches. You can keep more than that, but this will be sufficient. So at least there is a clear cover. Then to calculate the beam effective depth, so effective depth is the distance from the bar centroid to the opposite surface of the beam. So let me show you one by one. I'll spend a few minutes here. So একটা করে যাই, huh? Look at the left beam. The effective depth starts from the bar centroid. 4 bars are placed in a row, so centroids are here. Centroids. From the bar centroid to the opposite side of the beam. So effective depth is calculated here. You should take a calculator and see for yourself. So when you calculate the effective depth for this beam, what do you, how do you get it? You know the total depth is 24 inches. So total depth 24. So from 24, you subtract the clear cover, which is 1.5 inches. Subtract 1.5 inches. Then to reach the center of the bars, you need to subtract bar radius. So here the bar is number 7. Number 7 বারের রেডিয়াস হচ্ছে, ডায়ামিটার হচ্ছে 7/8 inches. সো রেডিয়াস হচ্ছে 7/16 inches, which means 0.4375. So you subtract this, and this is how you calculate the effective depth. Effective depth, no rounding. একটা দুইটা ডিজিট দিলেই চলে, but rounding is not required. So now you should try to get the effective depth of each and every beam that I have in this PowerPoint. For example, the next beam to the right side, you calculate the distance from the bar centroid. We have 2 rows of bars. Centroid must be here. So bar centroid থেকে to the opposite side of the beam surface is the effective depth, beam effective depth. So if the total depth is 24 inches, how do you calculate effective depth? What are the things that you subtract? You take 24, you subtract the clear cover, then you subtract a bar diameter. We have number 6 bars, so diameter of number 6 bars is 6/8. So you subtract a bar diameter, then you subtract half of the layer to layer distance. This layer to layer distance is 1 inches. Layer to layer distance, layer to layer, one inch if coarse aggregate is less than or equal to 3/4. But it will be 1.5 inch if coarse aggregate is less than or equal to 1 inches. So in our class, we shall always consider that the coarse aggregates are 3/4 inch downgraded, which means coarse aggregates, the largest coarse aggregate will have a size 3/4 inches, and there will be smaller sizes. So if the largest coarse aggregate has a 3/4 inches size, we will consider that layer to layer distance is 1 inches. So if layer to layer distance is 1 inches, we have half. So we subtract 0.5. Now I'm giving you 1 minute to understand how this D is calculated. Why don't you take a
Sir,
piece of paper?
Sir, can you repeat the half inches thing?
We are calculating the distance from the bar centroid. Centroid is here. Can you look at the centroid point?
Yes, sir.
So from the centroid, you calculate this distance, effective depth. So we do this calculation by subtracting a few things from the total depth. We know the total depth. The total depth is up to this level, up to the bottom level. Then what are the distances that you need to subtract? Number one, you need to subtract clear cover 1.5 inches. Then you subtract this bar diameter. Bar diameter is for number 6 bar, it is 6 by 8 inches. Then you need to subtract half of the layer to layer distance. If the layer to layer distance is 1 inch, half of the layer to distance is 0.5 inches. So this is how you calculate effective depth. Can you just have a look and try to understand? আমরা জাস্ট টোটাল ডেপথ থেকে একটু একটু করে সাবট্রাকশন করে করে বারের সেন্ট্রয়েডে পৌঁছাই। You just need to think what are the distances you need to subtract to reach to the bar centroid. আমি 1 মিনিট সময় দিলাম, এই দুটো একটু আন্ডারস্ট্যান্ড করার চেষ্টা করো।
Sir, like
Yeah.
for this math, you say that we have to subtract the diameter, but the previous one we just subtract the radius, bar radius.
In the previous problem, the centroid was located here at the midpoint of the single layer of burrs. But in the second problem, we have 2 layers of burrs. Centroid is located between the 2 layers.
Yes, sir, got it.
Got it? Okay.
Yeah.
At first, you need to locate the centroid of the burrs. Okay. Okay, I have a few examples. So next example, we will calculate the effective depth. So at first, you need to locate the centroid. There are 4 layers, so centroid must be here, right at the middle, right now? Do you find the dot that I wrote just now? আমি যে একটা dot দিয়েছি red color কেউ দেখেছো?
Yes, sir.
Okay,
Yes, sir.
good.
Yes, sir.
So এই dot থেকে you will calculate the distance to the opposite surface of the beam. So এই dot, you have to reach this dot from the top, because up to the top it is 36 inches. It is 36 inches. So 36 থেকে তুমি কি এখন সাবট্রাকশন করবে চিন্তা করো। You subtract 1.5 inches as clear cover. Then you subtract a bar diameter, which is 8 number bar, তো diameter হচ্ছে 8 by 8. Then you subtract this layer to layer distance 1. Then you subtract 1 more diameter 8 by 8. Then you subtract half of layer to layer distance 0.5. Again, I'm giving you like 1 minute to understand how the distances are subtracted one by one to calculate the effective depth from the total depth.
স্যার 0.5 টা স্যার জন্য কি
A point কি
0.5 টা স্যার আরেকবার একটু বলেন স্যার।
দুইটা লেয়ারের হাফ ডিসটেন্স না এটা শেষেরটা।
ও আচ্ছা আচ্ছা
আচ্ছা স্যার 8 বাই 2 বার আসলো কেন একবার?
দুইটা লেয়ার আছে না। If you want to reach the centroid, তোমাকে তো প্রথম লেয়ারও মাইনাস করতে হবে, সেকেন্ড লেয়ারও মাইনাস করতে হবে, তাই না?
ওকে স্যার।
You just need to know how you reach here, how you reach the center. প্রথমে তুমি সাবট্রাকশন করবা ক্লিয়ার কভার, তারপরে একটা বার ডায়ামিটার, তারপরে বারের লেয়ার টু লেয়ার ডিসটেন্স, তারপরে আরেকটা বার ডায়ামিটার, তারপরে হাফ অফ লেয়ার টু লেয়ার ডিস্টেন্স, তাই না?
ইয়েস স্যার।
আচ্ছা আমি এবার জুম করে দেখাবো, দাঁড়াও নেক্সট ওয়ান আমি জুম করি। Say we want to find the effective depth for this beam. First, locate the centroid, bar centroid. বার সেন্ট্রয়েড হচ্ছে এখানে,
এখানে
ঠিক আছে?
জি স্যার।
বার সেন্ট্রয়েড হচ্ছে এখানে, গুড। দেন টোটাল ডেপথ থেকে কি কি সাবট্রাকশন করতে হবে? ইউ উইল সাবট্রাক্ট দিস ক্লিয়ার
One
কভার
lane.
ফার্স্ট, এটা 1.5 ইঞ্চ মাইনাস করবা, তারপরে সাবট্রাকশন করবা একটা বারের ডায়ামিটার, তারপরে সাবট্রাকশন
10.5
করবা লেয়ার টু লেয়ার ডিস্টেন্স, তারপরে সাবট্রাকশন করবা একটা রেডিয়াস, তাই না?
Yes, sir.
Yes, sir.
সো এই যে দেখো টোটাল ডেপথ 36, ক্লিয়ার কভার, তারপরে একটা বারের ডায়ামিটার, লেয়ার টু লেয়ার ডিস্টেন্স, একটা বারের রেডিয়াস। নাম্বার 9 বার, তো নাম্বার 9 বারের ডায়ামিটার হচ্ছে 9/8। নাম্বারটা সেভাবেই দেওয়া হয়, সেটাকে 8 দিয়ে ডিভাইড করলে ডায়ামিটার পাওয়া যায়। দিস ইজ হাউ বার দ্য নাম্বার, বার্স দ্য নাম্বার।
Sir, bar number and number of bars, এটা কি কোশ্চেনে দেওয়া থাকবে?
মানে ইফ ইউ নিড টু ক্যালকুলেট দ্য এফেক্টিভ ডেপথ কোশ্চেনে দেওয়া থাকবে, আর তুমি যদি ইফ ইউ আর ডিজাইনিং দ্য বিম ইউ উইল ক্যালকুলেট ইট। We will show you, there are a few methods of calculations. I will show you in the next class when you come back after the vacation.
স্যার লেয়ারটা তো হাফ হবে, রাইট স্যার?
কি
স্যার লেয়ারটা কি হাফ হবে?
লেয়ারের হাফ কেন হবে? এখানে তো ফুল লেয়ারই দেখা যাচ্ছে, হাফ তো করি নাই। লেয়ার টু লেয়ার ডিস্টেন্স ইজ 1 ইঞ্চ, যে 1 ইঞ্চ দিয়েছে তো।
ওকে স্যার।
স্যার আমরা রেডিয়াস থেকে ক্রস সেকশনাল এরিয়া ক্যালকুলেট করতে পারবো না, এবং এটা তো স্যার ভাইস ভার্সা, রাইট?
রেডিয়াস থেকে ক্রস সেকশনাল এরিয়া ক্যালকুলেট করা যাবে না।
জি স্যার, ক্রস সেকশনাল এরিয়া থেকে তো আমরা রেডিয়াস ক্যালকুলেট করতে পারবো না, রাইট?
ডেফিনেটলি নো।
ওকে স্যার, থ্যাংক ইউ। ওকে
Okay, we have more examples. Now, this is a tricky issue. We have 3 layers of burrs, but the last layer has only 2. So how do you determine the location of centroid? Here, it is suggested that you do not have to accurately calculate the centroid. You will consider that all the bars have equal numbers of, sorry, all the layers have equal number of bars. You consider that all the layers have equal number of bars. So the center will be considered to be located here. আমরা মনে করব যে এখানেও আরো দুইটা রড আছে, থাকলে তো সেন্টার এখানেই হতো। So we'll consider that there are like, you know, center is located at the middle layer, মানে লজিক্যালি যেখানে হওয়ার কথা সেখানে। Then we calculate the distance. So from the total depth you will subtract, কি কি সাবট্রাকশন করবা? নাম্বার 1 ক্লিয়ার কভার, তারপরে একটা বারের ডায়ামিটার, তারপরে
Here.
একটা লেয়ার টু লেয়ার ডিস্টেন্স, সোজা হয় নাই, তারপরে বারের রেডিয়াস। First clear cover, then bar diameter, then layer to layer distance, then bar radius. So 1.5 is the clear cover, bar diameter কত দিয়েছি, নাম্বার 10, নাম্বার 10 হলে diameter হচ্ছে 10/8, then bar to bar layer to layer distance 1 inch, then radius হচ্ছে 10/16, diameter half. So this is how you calculate effective depth. Similarly, for the right example, centroid will be located here at the center of the middle bar. আমরা মনে মনে কল্পনা করব যে আরেকটা রড এখানে হয়তো ছিল, যদি নাও থাকে আমরা মনে করব যে এটা থাকলে সেন্ট্রয়েড যেখানে হতো সেটাই। So centroid is at the middle. So what are the things you subtract? You just, find the distances. First a distance, clear cover, then arekta diameter, then layer to layer, then radius. So I think I talked enough about the calculation of effective depth. আর করবো না, এটা একটু ফাইনালি দেখে নাও।
Yes, sir.
So, okay, so we are done with the effective depth. Our next concept is the reinforcement ratio. We denote it by the Greek letter rho. It is just a ratio. It means ratio between, basically it's the ratio between steel area to concrete area. Basically it is the ratio between the steel area to concrete area. So, but we calculate it as reinforcement ratio is equal to steel area divided by beam width times beam effective depth. So although we are mentioning that it's the ratio between steel area to concrete area, so we properly use the steel area in the equation, but as we calculate the concrete area, we multiply the beam width with the beam effective depth, not beam total depth. So this is the difference. So mathematically, Mathematically, this is the reinforcement ratio, AS by BD, rho equal to AS by BD. By the way, before I proceed to the calculation of reinforcement ratio, you need to understand that almost all equations given by ACI, NB, and BC uses this parameter to provide restrictions. So we need to understand this parameter properly, and we need to understand the implications. Number one, implications. A large reinforcement ratio means you have provided a lot of steel areas. So a large over-reinforced beams are discouraged and will never be constructed. We will always keep our beams under-reinforced. So we will always keep our beams under-reinforced, which means we will keep our beams under-reinforced, which means that always the reinforcement ratio will be smaller than a certain maximum value. We will see it when we will design our beams. We shall not provide a large reinforcement ratio. You understand, if rho is calculated as AS by BD, if AS is large, rho will be large. If BD is large, rho will be small. So we will always have a trade between AS and BD. We will always have a trade between steel area and concrete area. We cannot increase the steel area indiscriminately. That will give us a large reinforcement ratio, and that will make our beam over reinforced, which is bad. So we'll always keep our beam under reinforced, which will mean that we will keep the reinforcement ratio under a certain maximum value. Now, before we move further, let's see how the reinforcement ratios are calculated. It's quite simple because you already know how to calculate AS and how to calculate D. So the rest is very simple. It's just a mathematical thing. So in every problem, rho is calculated as AS by BD. We have AS, we have B and D. So it's just the ratio. So can you just have a look at the calculation of reinforcement ratios? I would also suggest that you have a piece of paper and a pen. Why don't you just do it by yourself? Before I go conclude the class, I'll give you a few assignments.
স্যার একটা কোয়েশ্চেন ছিল স্যার ওভার রিইনফোর্সমেন্ট নিয়ে।
What?
স্যার আমাদের এই যে বিডিটা আছে স্যার ডিনোমিনেটরে, এখানে তো স্যার আমাদের কিছু স্টিল বার যেটা আমরা কনসিডার করেছি সেন্ট্রয়েডের ক্যালকুলেশনে, ওইটাও আছে, আবার স্টিরাপের জন্য যে দুইটা স্যার মানে
No. Stirrup is not included.
ওকে স্যার, ওকে স্যার।
Stirrup is not included. Even if you have some bars on the other side, for example, in the first beam, we have shown 4 bars, but there must be 2 small bars to the other side just to hold the stirrups in position. we are not
Yes.
going to consider those two bars. No, we shall
Okay.
not consider them. We shall not. They will be there, but they are useless. Their whole purpose is to hold the stirrups in position. Our purpose name. Similarly, every beam will have two small diameter bars on the other side just to hold the stirrups in position. We are not going to consider them.
Yeah, sure.
Stirrups are also not considered. We considered the main bars that are resisting bending moments. That's our whole purpose. So you calculate AS only for the main bars that are resisting bending moment, and B and D, I think you already know how B is always assumed or given, and D is, how do you calculate D? Here, the reinforcement ratio is quite large. By the way, when you calculate reinforcement ratio, I would suggest that you take at least 4 points, 4 numbers after the decimal point. You take 4 digits. Huh? You always take 4 digits.
Sir, for the ratio, how do we know that it's under maximum value?
We will talk about it maybe 3 classes from this class. After 3 classes from this class.
Okay, sir.
Yeah. We'll spend at least 2 lectures on this issue. So, you have B, you have D, you can calculate BD, and you also have AS. So I think that's it for today's class. We will, I think the formal lecture is finished by now. Let me see if anything is left behind. Gross concrete area, it is BH, but that is something we do not use in our calculations. So we talked about bars, bar steel area, bar steel bars means you calculate steel area, which is denoted as AS. We talked about beam effective depth. Effective depth is always denoted by D. So in your reinforced concrete class, you will always say D. D always means effective depth. So I'll give you a few assignments now. Assignments ki দরকার আছে? Quite simple.